Okay, so today we're going to talk a little bit about energy and gravitation. First I want to start off with a little bit of a follow-up to the other day when I was talking about law of universal gravitation. One thing I didn't mention was superposition, which actually is quite important. And we're going to see it again when we get into energy. So now, a basic concept of superposition, okay, and what superposition is what happens when you have more than just the one force, more than the one body that's contributing to a gravitational field. So now, let's just say that we have a mass here like this, and another mass, I'll call that M1, another mass over here, which I'll call M2, and I've got my little object over here, little m. Okay. This will be, I'll call this R1. I'll call this R2. Okay. Now, superposition says that the force on the little mass is going to be the force due to 1 plus the force due to 2. And that is a vector summation. So we'd have to know what the angle theta is here and do some calculations. Now, they're both going to attract. Okay? This one will attract in this direction. I will not, excuse me. This one will attract in that direction. So you're going to get a result where the attraction goes off somewhere in between. Okay? So now, and the force of each one, so the force on one would equal G big M1 little m over R1. These are the magnitudes, but we'd have to do some vector addition to actually do that. M2 little m over R2. Okay? Now, if we have them lined up like we have, let's just say we have the sun and the Earth with the moon over here, well, now we can do that calculation pretty straightforward. I think I might be running off the page there. Let me move that over. We've got the sun, the Earth, and the moon. Okay? Well, in that case, we could do it, and we wouldn't have to worry about the vectors so much. Okay? We could also see situations like this: sun, moon, Earth. Okay? Sun pulls this way, Earth pulls this way. Okay? Now, the sun has a lot more mass, obviously, than the Earth, but the Earth is also significantly closer. And when you look here, we've got the r squared. Because we got that r squared term, that distance plays a much bigger role than the difference in the mass. Okay, they obviously both mass and distance play a role, but the Earth's mass is much smaller than the sun's mass, but the Earth's distance is much smaller than the sun's distance to the moon. All right. So now, potential energy. One thing about potential energy that we've always done, okay, gravitational potential energy, we've always kind of assumed that we're near Earth's surface. We've got a little mass here. It's a distance h above. Okay, and we'd say that the potential energy due to gravity was equal to mgh. There's nothing wrong with that. Okay, but there's a couple things that we have to take note of. First of all, Earth's gravity is constant through there. It's really not. There's a very slight differentiation between, say, here and here, but it's negligible compared to any inaccuracy of measurement. But now, if I start looking at the Earth here, and I'm going from, say, here to here. Well, now I've got a much, that distance, okay, that it's away from Earth really does come into play, okay? It really does make a difference whether or not you are here versus here. There's a different force, okay? We can't use potential energy the same way because potential energy is a measure of, you have to look at the force, and the force is going to change between here and here. So now, we still have to set a zero for gravitation, for potential energy. When we would do these problems, when this would come down here, we would say that the potential energy at our lowest point was always equal to zero. Potential energy was greater when it was further up. We want to keep the fact that potential energy increases as you get away from Earth. We want to keep that. But we're going to lose that potential energy is equal to zero at Earth. Because then we say far away, well, potential energy would look like it's going towards infinity. So now, what we're going to do, we're going to set it up a little bit differently. Okay? We're going to say that far, far, far away from Earth, here's Earth, far, far, far away from Earth, this is far, far, this is infinity, by the way, it's really not, obviously. But we're going to say that this is infinity. Far, far, far away from Earth, okay, we're going to set the potential energy equal to zero. Okay? We have to pick some spot to be zero. So let's define it to be in a spot where that is infinitely far away. So we're going to say that where r is equal to infinity, or keep math teachers happy, approaches infinity, okay, the potential energy equals zero. But I said that when it gets closer to Earth, the potential energy decreases. I'm starting off at a potential energy of zero. How can I have potential energy decrease as I get closer if I'm starting off at zero? Well, potential energy due to gravity is always negative. Wherever you are, no square there. Okay? Potential energy is negative. It's always going to be negative. Negative G m1 m2 over r. Okay? Because as I get closer, so when I'm right here, this has a little mass. I'll call this m2. I'll say that this planet or whatever it is has a mass m1. They could be two planets, two suns. It could be the moon. It could be a human satellite, whatever. This R, by the way, goes to the center of mass of the planet. So now, that's going to be R. This is M1, M2, and M1. Okay, so the potential energy between these two is going to be negative G M1, M2 over R. Negative. That's the key. Is negative. So now, we're going to use this quite extensively in a lot of the problems. But one thing that we want to talk about here is if we have multiple planets. So let's just say we take a look real quickly here. We're not going to come up with a number. Let's just say that we have the Sun three-body problem. Now, there's lots of things that we can't figure out about a three-body problem, well, at least very easily. And we've got the moon here. Okay? There's a lot of things that we can't figure out about a three-body problem, but potential energy doesn't have to be one of them. Okay? So now the sun here, we've got a potential energy between the Earth and the sun, between the Earth and the moon, and also between the moon and the sun. So the potential energy is going to equal potential energy between sun and earth plus the potential energy between sun and moon, called SM, plus the potential energy between earth and moon. Okay? So a way that we could come up with a typical problem, okay? If I call this, and just move this over here so you can see it a little bit better. If I call this R SE for sun and earth. Remember, potential energy, you don't care about direction. The center of masses. I'm going to call this right here R Earth Moon EM, and this will be R SM for sun and moon. It doesn't, remember, direction doesn't matter when we're talking about energy. Energy is a scalar quantity, not a vector quantity. So now, the potential energy here would equal negative G mass of the sun, mass of the earth, over R SE, minus G mass of the sun, mass of the moon, over that distance between them, sun and moon, minus, I think I'm going to run off here, over here, minus G mass of the earth, mass of the moon, over that distance. Okay. I'll step off camera, make sure everything's still in the shot. So now, all we do is add them together. All right, all we have to do is just add those quantities together. And let's see here. I think the very bottom got cut off there a little bit. Let me just drop that down. All right. So now, we just add those quantities together. They're all negatives. We can pull the negative out if you want. That's fine. It doesn't really make a difference. But potential energy is nice. So if I put in a whole bunch of objects, we can calculate the potential energy of their masses because they have mass. A quick proof of potential energy. I'm not going to go through a proof of adding these together, but just a proof of the fact that potential energy is equal to negative Gm1 m2 over R. So now, let's say we have an object that we're going to move from planet starts out a distance R away. A lot of times that's going to be that R is going to be from the surface of whatever object. And we're going to move this out towards infinity. Okay? Well, a couple things to note. We're going to have a change in distance that our dr as we go out here. Okay, R is the starting distance. Okay? Little r is going to be the distance at any moment in time. Our dr is going to move us from here out towards infinity. The gravitational force is going to pull back the other way. So the force of gravity pulls back in the other direction. So let's consider the work that's required to move this object from R out towards infinity. Well, now, the work that's required is going to equal, going back to earlier in the year, f of R dotted with dr. Okay? At the time, we probably used f of x dx. Okay? Typically, when we're talking about planets, we use R instead of x. And this is going to go from some starting point R, big R, to infinity. Well, a few things here. F of r is equal to negative g, should be positive. I'll say big M, little m, over r squared, whatever that distance is. Okay? So if it's here, it's going to be a different r. If it's here, it's going to be big R. That little r would be big R. Okay? This has a mass big M. This has a mass little m. Okay? Now, we have to get this dot product. Okay? This is going to, we want to convert that dot product. So we're just going to call this f of r dr cos theta. Now, the angle between dr and the force of gravity, theta, is equal to 180 degrees. So the cosine of theta is equal to negative 1. So now the work that's required is equal to negative, keep it in the integral for now, the integral of f of r, which is g big M little m over r squared, dr cosine theta is negative 1. I just put the negative out front here. Big G is a constant. The mass of the planet is a constant, we hope. The mass of our object, again, a constant, we hope. It actually does, if we're talking about a rocket, actually does change a little bit, but we have to be careful there. So this is negative big G, big M, little m, integral of dr over r squared from big R to infinity. So, I do that integral. Integral of 1 over r squared. So I kind of keep aside here my negative g, big M, little m. Integral of 1 over r squared is going to be negative 1 over r. So I get negative 1 over r as r goes from big R to infinity. Negative, negative becomes positive, positive. So I get the work is equal to big G, big M, little m, over, now I plug in over infinity, minus big G, big M, little m, over r. Anything over infinity approaches 0. So our work here is equal to negative big G, big M, little m, big R. Okay, so let's get this in terms of, I want to make sure that I get this in terms of potential energy. Okay, work is good, but I need it in terms of potential energy. So now, what I'm going to do is compare potential energy and work. We talked about that earlier in the year. Okay? Remember, we said work was equal to a negative change in potential energy. So in this case, this is going to go from negative, okay, negative, it's going to be U final, which is U at infinity, minus U initial, which is the potential energy at R. Okay? So now I have negative, now I can flip these two. The work is negative, big G, big M, little m, over big R, is equal to, okay, U at infinity, we said was potential energy at infinity, we said was 0. Negative, negative becomes positive, positive. Potential energy at R. And we just reverse it around. My potential energy at R is equal to negative Gm M over Kr. So that's just a quick proof. It is good to see. The reason why I do this proof, I want you to see some of the positive and negative factors where they come in from. Okay, I think it helps to understand that what we're really talking about when we're talking about potential energy is the amount of work that's required to bring in an object from infinity to R, or that would be, and that's negative, okay? Or if we're talking about the work, because work is negative, okay, the work required to move it out to infinity, as far as the gravitational field is concerned. Now, going from there, we want to talk about escape speed. This is why I didn't do escape speed before we left. That would have been a little crazy. Okay, escape speed really what that does is say, all right, we want to go, okay, it's the a V0 required. V0 required to move to infinity with no extra push. In other words, no other forces being applied. So I have to have a certain amount of kinetic energy that gets converted to potential out at infinity. Okay? This is really peaky. Potential energy initial, kinetic energy initial, because this can't change, the amount of energy it can't change. It's not colliding with anything. Okay? We want, now first of all, we want to get just out to infinity. So if we just make it out to infinity, we're saying that at infinity, now I can come to rest. So I'm going to say that my kinetic energy is equal to 0. At infinity, I have defined my potential energy to equal 0. Okay? My potential energy initially is going to be negative G, big M, the mass of the planet, whether it's the sun or some other star, or whatever planet we're talking about. Okay, this is going to be the mass of our object that is going to escape from there. Divided by, usually this is going to be the radius of the planet itself. Plus my kinetic energy initial, 1/2 m v initial squared, will equal, if this is 0 and this is 0, well, the whole thing in there is 0. Now, I'm going to call this, so V0 I'm just going to call V escape. The m's drop if I divide both sides by m. Okay. Multiply everything by 2. I wind up with V escape squared is equal to, I bring this over, G big M over R times 2. So my escape velocity is equal to square root of 2g n over r. So now, again, that r could be the radius of the planet, that big M. And also notice that it doesn't depend on the size of the object that we're talking about. It only depends on the size of the object we're escaping from. They give a couple of escape speeds in your book. Earth's, our moon, our escape velocity is 2.38 kilometers per second. Earth is 11.2 kilometers per second. Sun is 618 kilometers per second, okay, from the surface of the sun. From Sirius B, which is a white dwarf, Um, it is 5,200 kilometers per second. If you're talking about a neutron star, which is the collapsed core of a star after a supernova, it is 2 times 10 to the fifth, so 200,000 kilometers per second. Additionally, if you want to put that in meters per second, that's 2 times 10 to the 8th meters per second. The speed of light is 3 times 10 to the 8th meters per second. So a neutron star is not quite a black hole. It's almost there, though. Once you reach the point where your escape velocity is over the speed of light, that is, by definition, what a black hole is. Also, just a little bit about a neutron star. They say that the radius is about 10,000 meters, so it's about 10 kilometers. So the diameter would be 20 kilometers, which would basically be, you could fit it basically entirely within Monmouth County pretty easily. So yeah, that's about 12 miles wide. So imagine something more massive than the sun, about the mass of the sun, that has a radius of about 12 miles. Okay, that is an incredibly dense object. Okay, a spoonful would weigh more than a mountain. To give you an idea of how much gravity has just absolutely crunched this object together. Okay, a neutron star, they call it a neutron star because all the protons and electrons are basically shoved together. So they shove the electron back into the proton, which converts it into a neutron. Okay, that is a very, very dense object. Okay. All right, so now moving on from escape speed. Kepler's laws. All right. The thing that is amazing about Kepler, okay, at the dawn of the scientific revolution, it wasn't so much that he took the Earth away from its position as the center of the universe. Okay, he put the sun there. Not really even being sure about that, but knowing that the Earth rotated around the sun, or at least, as he put it, it was a mathematical trick, just to see, to make sure that it could work. It was simply a model to see how this could work. Whether or not he actually believed that it was just a model or not, it's probably a pretty safe bet that he didn't believe that. He truly believed that the sun was the object that the Earth rotated around. What I find even more incredible than that is that he was able to make all of these assumptions that I'm about to go over, these Kepler's laws, using only very, very basic equipment. Okay. First of all, he said all orbits are elliptic in nature. So anything that's in orbit around something else, okay, follows an ellipse. He didn't just observe that it was circular, which the planets around the sun are almost imperceivably not circles. Okay, they are circles as far as the eye could see. He was able to make calculations so precise that he understood that they were not quite circular in nature. But he observed that all orbits are elliptic in nature. Now, the other crazy thing that he did, this is what kind of blew my mind. He said that all objects sweep out the same area in the same time. So if I have this object that's rotating around in this direction, okay, and it gets over here, okay, it'll carve out this area in a certain period of time. So I'll call this A1 and T1. At that same time, as this rotates around over here, he observed that the time that it took to go from over here to here, call that delta T2, if delta T1 is equal to delta T2, okay, the times are equal, just mathematical reason, that those areas also equal each other. Okay? Now, first of all, calculating the area of an ellipse is pretty complicated. Okay? But even more so, what he didn't realize at the time was that as far as heavenly bodies are concerned, they actually practice conservation of angular momentum. Okay? You can look in your book for a proof on it. But this is, so what this is saying is, when it's out here, okay, it's going to move more slowly. If you're in here and you're going to sweep out this area right here, okay, notice that it has to cover a wider distance, okay? This is narrow, this is wider, okay? That you're going to move more slowly out here than if you're in tight. So the closer this object that's orbiting around this planet, okay, when it's in close, it moves faster. When it's further away, it moves slower. That's not hard to see, the fact that when it's faster here and it's slower out here. What is incredibly hard to understand, that he was able to figure this out, was that he was able to calculate these areas. Okay? I find that fascinating. It's not just that he could see that, oh, you're faster here and slower here. He recognized that it was the areas that were equal. And really what that is a proof of is conservation of angular momentum. The third thing that he noticed was that for any object in orbit around some other object, the period of its orbit squared is proportional to its radius cubed. Again, not just doing this for circular things. Okay? Or if you're talking about elliptical objects, you would call it the semi-major axis of the ellipse. Okay? Now, that's really easy. This is a proof of conservation of angular momentum. This can be proved with Newton's second law. So what Kepler did with just looking out at night, okay, think about how brilliant this guy had to be. He just looked out at the night sky and kept incredibly precise recordings. Okay, they had observatories at the time, but they were, you just kind of sit there and you kind of be able to position yourself around so you could get your angle measurements and everything like that correct. And remember that it rotates once every 24 hours, so you had to take that into account as well. But for heavenly bodies, essentially, he proves conservation of angular momentum and Newton's second law. Let's see how the Newton's second law thing works. That's not a hard proof. So for Kepler's third law, okay, we're going to just look at force on the object is equal to G, big M, little m, over r squared. Okay? Now again, if you're talking about ellipses, you can talk about semi-major axis A, but we're going to use, for circular orbits, it's a lot easier to take a look at. So now, this is the force. Force is equal to mass times acceleration. So now, this is on the object that's orbiting. So now, little m's drop out, big G, big M over r squared equals the acceleration. Acceleration for an object going around in a circle, omega squared r. Okay, something we haven't talked a whole lot about this year. Okay, omega is equal to 2 pi times the frequency that it makes its path, or 2 pi over the period. So we're going to use that period there. So now, I'm going to divide both sides by r. So I have gm over r cubed is equal to omega squared, which is 4 pi squared over t squared. Well, we can cross multiply or just flip it over, however you want to put it. What this is going to show us is that we have t squared is equal to here. Okay, so we're going to wind up with 4 pi squared over gm times r cubed. Okay. Okay. Now, pi is a constant. G is a constant. The mass of the planet or whatever object that is orbiting around, that's constant. This whole term is a constant. That means that t squared is proportional to r cubed. A couple other things. We want to take a look at the kinetic energy of an orbiting object. Again, we're going to do it for circles, but we'll take a look at a couple examples where it's not circular, because they are important, and they've been on the AP exam in the past, and I think it's just interesting to go through it. So I have to be able to go over an AP problem tomorrow on this. All right, so now, we know that the potential energy is going to equal negative big G, big M, little m, over r. Kinetic energy for any object is going to be 1/2 mv squared. So now, we want to take a look at a case where it's going around in a circular orbit, and we want to compare it to okay. We don't want to just focus on this. We want to look at it in terms of our potential energy. Okay. So for now, orbital energies. Okay, so now we know that big G, big M, little m over r squared, and I'm going to assume that's the surface of the planet, will equal mv squared over r. R drops out. Little m little m we're going to keep. We could drop out if we wanted to, but we want to get the kinetic energy. So what I have here is that for an object in orbit, circular orbit, I have mv squared is equal to g m over r. How could I get kinetic energy? Multiply both sides by 1/2. Multiply both sides by 2. My kinetic energy for an orbit is equal to big G, big M, little m, over 2r. Okay? Now, if you're talking about, you could then say that the kinetic energy is equal to negative potential energy over 2. Okay? But we have to be careful because when you're talking about elliptic orbits, kinetic energies are not constant. But we can look at the total energy. The total energy is going to be constant. Total energy is potential energy plus kinetic energy. So my total energy is equal to potential energy, which is G, big M, little m, over R. Can't forget the negative. Kinetic energy is positive big G, big M, little m, over 2. Then little r. Over little r. So my total energy is equal to negative G, big M, little m, over 2r. Okay? This is constant for anything in orbit. Now, if we're talking about something that's going around in a elliptic orbit, we can say, and this is constant, negative G, which we're not necessarily proving here, but just taking it by analogy, over A, where A is the semi-major axis. Okay? And if you remember back to your pre-calc days, that is definitely not a very good ellipse. Okay? This is your semi-minor, this is your semi-major. So A is this distance right here. That is your semi-major axis. Okay, that is an extremely long lecture. I hope we broke it up a little bit. But anyway, we're done. I will see you tomorrow. And if I don't, have a Merry Christmas, Happy Holidays, Happy New Year.